So I'm here at the EGU 2026 with Scott Bolton, the principal investigator of NASA's Juno mission to Jupiter and its moons. And they've just had a fascinating press conference, which uh, Scott and his colleagues here described Juno's latest discoveries out at after 83 orbits. And so you're at the Southwest Research Institute in San Antonio. I just want to make that clear. Um, so give us an overview, pre-launch, of some of the questions about Jupiter compared to 10 years later. Uh, what are like the overarching discoveries that Juno has made in the system?
So prior to launch, we were trying to understand how Jupiter was formed and evolved, and a lot of that had to do with what the structure inside was like. Beneath the surface that we can see, is there a compact core of heavy elements in the center, or is it just hydrogen and helium gas with a little bit of enrichment going all the way down, and there's no boundary to the core? And what we found out is actually neither is exactly true, that Jupiter has a very large diffuse core, dilute core, and there may be a small compact core, we think, in the very center, and we've been using machine learning and AI to kind of resolve those results. But that was certainly a major discovery and not anticipated prior to launch. I mean, how Jupiter is made that way is still hard to come up with a model that actually works to build a Jupiter the way we see it. We also discovered that the atmosphere was not very well mixed, even deep down. So we have a special instrument that looks down hundreds of bars, so well below the weather layer, the condensation of ammonia and water. And prior to Juno, it was thought that once you drop below that, Jupiter is getting warmer as I go down. So if I drop below the part where water is ice and then liquid and it goes into gas, it was thought that everything would be well mixed. It turns out it's not. It's not well mixed at all, and that was a big surprise. It's not clear exactly how that's maintained, but that couples into sort of a theme that Jupiter is not simple. It doesn't work with the simple physics and simple scientific ideas that we like to think of often, and that it's very complex. Things are not mixed. The interior is not mixed. There's this dilute core that has gradients in it. And so I think we have to go back to the drawing board and really investigate and realize that nature is more complex than our simple models.
And how does how does what we've learned from Juno impact our models of our own solar systems formation, and what we've learned about exoplanetary systems, which we started out have a lot of hot Jupiters, now they're warm Jupiters, and now we're looking for real Jupiters at 5 AU or 12 years or 12-year orbits around other
Right.
sun-like stars.
And I believe those exist right now. It's hard for us to detect those with the current telescopes, but so there is something that we would call a selection effect. You can see, you see what you can see, and not necessarily everything that's there. But I think when we think about Juno's discoveries and how they impact our thoughts about the solar system, Jupiter is very much our example, our archetype of a giant planet throughout the cosmos. And so if it works differently than we think, then likely the exoplanet systems are building giant planets like exist very much the way they exist here. And so I think that's changing our ideas, or more importantly, I think that we've reached a point where what we're learning in the solar system can help understand the exoplanetary systems, but exoplanetary systems can also turn around and help us learn about our own solar system. So as an example, we get to look at our solar system in much more detail than somebody that's studying, another star system far away, because we can actually send spacecraft, we can collect data, we can really get detailed measurements. But we're only seeing our solar system today, the way it is now. When we go back and we look at other solar systems, we see a whole distribution of them in different stages of evolution. Some are young, some are older, some are in the middle. There's a role of some sort of dust rings out there that help form that. I think that we've reached a point where these two fields can actually learn from each other.
Well, thank you so much, Scott, for your time today and for your words during the press conference, and we look forward to hearing more data.
Thank you for helping to share the excitement of space exploration with the public.